The assigned product for this project was a steel commuter bike frame. To help simplify and streamline the material selection process, a diagram of the frame online was chosen, as pictured here. We assumed that the maximum force any member could take would be the entire weight of the rider. So we chose to consider the force behavior of the largest member on the frame. This component is the down tube, which has a length of 618 millimeters. Even though Figure 3 has a specified outer and inner diameter, cross-sectional area will be used as the free variable for the three material performance indices, aka MPIs. The maximum force that will be applied is 981 newtons, from an upper bound of 100 kilograms, as an average weight of an overweight person.
Initial design notes were to minimize weight, cost, and strain, in turn maximizing Young's modulus. 0.2 kg comes from an estimation of the largest member on the bike frame. $200 is a competitive price for a steel frame on the market. A section length of 618 millimeters was taken from the largest member of the frame, and the deflection was chosen as an amount that would not alarm the user. Limiting factors for material selection include the numerical constraints in the previous slide, as well as the ability to withstand the cold, formability, weldability, and corrosion resistance from salt water and otherwise. Negative 60 degrees Celsius is the record low for temperature in Ontario. As such, it is used as the lowest temperature the material must be able to perform normally in. Corrosion resistance from salt water specifically is necessary due to the road salt used to de-ice roads in Ontario, and thus will be present in the environment that the material will operate in. In CES EduPack, these factors have values like good and poor. As such, we chose the good and excellent values to ensure a suitable material.
As shown on the slide, the objective for this MPI is to minimize mass. The maximum allowable value for mass, as mentioned before, is 0.2 kilograms. The functional requirement for the member is to be able to handle a load of 981 newton, and the geometric constraint is a length of 0.618 meters. As a result of manipulating equations for yield stress in terms of force and area, as well as mass in terms of area, length, and density, we're able to create a constant from the numerical constraint called S1, which represents the y-intercept of the MPI. Taking log of the previous MPI equation and plotting it on the log-log graph of density versus yield stress gives a line. All materials above this line are satisfactory. All groups shown in turquoise are stainless steels, and only materials that meet the general limits on the previous slide are colored. The rest are grayed out. Considering the logarithmic behavior of the plot, the slope of the MPI is the inverse of exponent in the MPI, which in this case is 1. Zooming in, we can see that all steels that fit our categorical limits have roughly the same density, but varying in strength. The most optimal choice for the bike frame in this case, if we were only considering this MPI, would be the custom 455 H950 martensitic stainless steel.
Constraint values for the second MPI were the same as the first. However, this time we will be optimizing for minimum mass, and also have a functional requirement on deflection to be less than 1 millimeter at maximum limit. The same method for calculating the MPI can be shown here, this time optimizing for Young's modulus over density. Using the same plotting process as before for Young's modulus versus density, the turquoise sections are the stainless steel, both acceptable from the MPI and the categorical limits. With this MPI plotted in CES and zooming into the acceptable materials, we see that AISI 434 annealed ferritic stainless steel is the highest performing material above this index.
The objective for the third and final MPI is to minimize cost. The cost of the total frame must be less than $200, so therefore the cost of one member would be 200 divided by 6. since there are 6 members in total. The functional requirement and geometric constraints are the same as the first MPI. The calculation follows the same method as previous MPIs and are outlined in detail in our supporting document. The equations used are cost per volume in terms of cost and volume, yield stress in terms of force and area, as well as volume in terms of area and length. Plotted in CES, we see that AISI 410 steel is the best performing cost versus yield stress material.
Some other criteria that we had for limiting our selection was to choose a material with a non-body-centered cubic or BCC crystal structure, because BCC materials have a brittle to ductile transition temperature, which causes them to fail under extremely low temperatures. Another factor in the choice of material would be the fatigue strength limit. CES has the fatigue strength limit set at 10 million cycles. An optimal material should retain a large portion of the original yield strength by that many cycles to ensure it will not fail under a small usage time.
To summarize, the highest performing common material amongst the 3 MPIs was AISI 410 steel. Commonly used for rings and cutlery, this martensitic stainless steel is suitable for a steel bite frame because of the strengthening due to tempering. Additionally, the drop in strength after 10 million cycles of 64% is on the higher end of strength dropping amongst other stainless steels. AISI 410 steel needs to be machined in its annealed state, so that the members will have to be made, fused together with welding, and then the entire frame will need to be tempered according to this heat treatment schedule. Notice that the tempering temperature and times are both at the higher end as compared to the range of values shown in the supporting document. This is because we require a harder temperature to ensure strength. Annealing causes grain recovery and removal of cold working. Tempering causes internal stresses, increasing material toughness.
For coating the bicycle frame, we chose thermoset polymer powder coating. This does not require solvent like liquid paint. It is applied through electrostatic charges and cured with heat. The reason for choosing this type of coating is because it is relatively more durable than paint coating. The cross-linking of the polymer chain molecule during the process of heating forms a permanent matrix and contributes to its scratch and mar resistant properties. These properties are important for a commuter bike because they're used frequently and encounters impacts and abrasion constantly throughout their lifespan. Furthermore, powder coating is more cost-effective. The excess polymer powder that did not adhere to the part can be reused. Also, it does not release volatile organic compounds, which makes it more environmentally friendly compared to paint coating. The process of thermoset powder coating involves part preparation, powder application, and curing the coat. Firstly, it is important to clean and strip the bicycle frame for a long-lasting and successful powder coat. In the case of steel tubes, shot blasting is an appropriate procedure to remove oil, grease, metal oxide, and other impurities. Then the polymer powder is applied to the frame through an electrostatic spray gun, which imparts positive charges on the powder and sprays them onto the grounded frame. The powder will naturally adhere to the frame because of the difference in charge. After the deposition of powder, the part will be put into the oven for curing. Finally, after the frame cools down, it is ready to be assembled to the rest of the bicycle parts.